So first of all, thank you very much to the organizers for organizing this. It's a lot of fun. Glad to be here. And thank you all for staying. I know it's been a long day, so I appreciate you, your willingness to come hear me speak. Okay. So what I'll be talking about today is joint work, part of it at least, with Mihai Fulger and with Jian Xiao. And I wrote down the notation on the board. So throughout the talk, X is going to be a smooth projective variety over C. Most of what I say will be more general, but this is the only setting in which everything works. The dimension of X is always n. I will never write that again, because I'll forget. So the dimension of X is n. And then instead of using the usual MMP notation, I'll just write what I mean. So the pseudo-effective cone of curves is written with F. The Neff cone is written with Neff, and so on. Okay. So first, let me start off by reminding you of some things that you know already. So the volume of a Cartier divisor let's say L is, so I'll denote it by vol of L, and it's the lim sup as m goes to infinity of the dimension of the space of sections of m times L against m to the n, where, as always, it is the dimension of X, and then rescaled by n factorial. So this is a familiar constant. We've seen it several times already. We'll see it several times more. So we're going to be interested in the theory of the volume for a little bit. So let me start off by reminding you that the volume is an invariant of a numerical class. Okay, one of its basic properties is that it doesn't depend on the divisor only, but it only depends on the numerical class of the divisor. So it descends in a natural way to the lattice inside of n1 of x, consisting of classes of actual divisors. Okay, and so from now on, we're almost always going to think of it like this. We'll just think of it as, you know, some class on a lattice inside of a finite dimensional vector space. Okay. If we're thinking about it like this, it makes sense to start discussing some of its analytic properties. So let's see what those are. The first theorem, so different pieces of this, I believe, are due to Demailly, Ein and Lazarsfeld, or to Buxom, Farver and Janssen, or to Lazarsfeld, Mustatsa. Okay. And this says that vol extends to a continuous weight n homogeneous function on all of n1 of x. Okay, so a priori is just defined for the lattice, but you know, it scales well, and then you can make sense of it for any Q class. And then it's locally uniformly continuous, so it extends to a continuous function on the entire R vector space. And furthermore, it is continuously differentiable on the interior of the pseudo-effective cone. Okay, so we obtain this function with some nice analytic properties, and you know, I think, again, you guys probably know this, but C1 is the best you can do, even in very simple examples like blowing up P2 at a point. The volume fails to be continuously differentiable. Okay, so there's actually more to say. So again, I'm going to sort of mash several theorems together. The first is due to Lazarsfeld, and then the second is done in joint work with Jian Xiao. So this says that the volume is n concave on the interior of the pseudo-effective cone. Okay, so let me explain what this means. So what I mean by this is for L and D big divisors, we have an inequality that the volume of L plus D to the 1 over n is at least the volume of L to the 1 over n plus the volume of D to the 1 over n. Yes. Well, yes. I think so. Yeah. So this is somewhat stronger. So what's going on here? So the n in n concave is referring to the fact that you take the nth root, and then this is saying that the nth root of the volume is concave. So it's not too hard to rearrange this to look like the usual definition of a concave function. Okay, but it's a little bit easier to state it like this. So we'll just go with this. Okay. Furthermore, so equality is achieved if and only if the positive parts p sigma of L and p sigma of D have proportional numerical classes. So let me just point out, so here p sigma denotes the positive part of the Nakayama-Zariski decomposition, which again I suspect is probably familiar to everybody. Okay, so not only is the volume n concave, but you can exactly capture the failure of strict concavity. And this is done by the Nakayama-Zariski decomposition. Well, in fact, there's many different ways of defining Zariski decomposition in codimension 1, and for big divisors, they're all the same. So you can choose which one you like. Okay. So again, we're going to systematically take this perspective as well, that the Zariski decomposition is somehow encoding the failure of strict concavity of the volume. Okay, this will be a very helpful perspective for us. And so in particular, this means that the volume is strictly n concave on the movable big cone. Okay, just follows immediately. Okay, so again, this is sort of a well-known story. And we see that for divisors, we have this really sort of interesting interplay between sort of analytic properties on the one hand and asymptotic geometry on the other. So loosely speaking, that's going to be our goal for today, is for curves to relate, on the one hand, the structure of the pseudo-effective cone, and also some kind of asymptotic geometry. And then thirdly, we'd like to understand maybe some sort of convexity theory. Okay, so we'd like to develop this nice picture for divisors as much as we can in more generality. Let me point out that long term, really what I think would be interesting to do is to do this for arbitrary cycles. Not just in dimension 1 or codimension 1, but in arbitrary codimension. So there's a lot of subtlety when you work with higher codimension cycles, But again, part of what I talk about today will hold in this generality. So I'll highlight that when it comes. But the most rich theory that we have right now is for curves. So we'll focus on that case. Okay. So let me start off with a few reminders about convexity. So let's start with some basics. The Legendre-Fenchel transform of a real valued function f, so here f is just a function from R to R, which is convex. So the goal of the Legendre-Fenchel transform is to relate two objects. So first, it relates to differentiability of f in some way to the strict concavity or the strict convexity of its transform f tilde. Okay, so this is some construction from real analysis. And what we'd like to do is we'd like to sort of look at an analog of this in our setting. Right? Whenever you have a concave function, as this theorem is sort of illustrating, you should try to understand the failure strict concavity for it. So I'll tell you what this is in a second, but so in our setting, we need to work with some sort of duality, just like the classical Legendre-Fenchel transform. And the duality that we use is the duality of the Neff cone of divisors with the pseudo-effective cone of curves. Okay. If we'd like to understand the pseudo-effective cone of curves, we need to use this one. It's also interesting to study the pseudo-effective cone of divisors, in which case we'd use the other natural duality. But for today, we're going to stick with this one. What's that? This is a Legendre-Fenchel transform. So something, yeah. So I'm going to write down what it is for us right now. So this is a definition of my co-author Xiao. So this is for a class in the interior of the pseudo-effective cone of curves. We'll define its volume to be the following thing. So I'm going to denote the volume of a curve with a hat. So this is just to remind us that it's the volume of a curve and not the volume of a divisor. Okay, so we'll define the volume of alpha to be the infimum over all ample A of alpha dot A over the volume of A to the 1 over n, this whole thing to the n over n minus 1. Okay, so this is known as the polar transform. It's the analog in our setting of the Legendre-Fenchel transform. But anyways, so let's take a look at what this is doing. Okay, so we're starting with the class alpha, and we'd like to measure how big it is by comparing it against ample divisors A. Now, of course, if you rescale the ample divisor A, you can make this intersection number as big as you like, right? So then we have this this other invariant, which this is now linear in rescaling of A, so it exactly cancels out the rescaling factor here. Okay, so at least this is some sensible quantity measuring how big alpha is against ample divisors A, and then we have some sort of Holder conjugate exponent up here. Okay, so this is the definition of the volume. So it follows, again, just from some sort of general analytic theory, that this function is, well, it's continuous. In fact, it's C1, again, on the big cone. It's homogeneous of weight n over n minus 1. And it's also n over n minus 1 concave, but not strictly. Okay. So, well, I'll say a little bit more about this in a sec. So we see that it has the same sort of nice analytic properties that the volume function for divisors does. Let's start off by looking at a couple basic examples. Okay. So let's suppose that H and A are ample divisors. Then the Khovansky-Tessier inequalities tell you that if you look at h to the n minus 1 dot a, this is at least as large as h to the n minus 1 over n times a to the n to the 1 over n. Okay, this is a classical Khovansky-Tessier inequality, or one of the versions of it. And then if you compare this to that, if you just sort of divide by this to the other side, this shows that vol hat of h to the n minus 1 is equal to h to the n. Okay? So the effect of this vol hat function, when you do it on a complete intersection of an ample divisor against itself, it's in some sense taking a root. You know, it's returning the original ample divisor in some sense. Okay. Let's look at another example. So well, this is a non-example. Let's suppose that x is excuse me. Let's suppose that x is toric. Okay. This function is easy to compute. You know, up to taking the infimum, I guess. So volume is not hard to compute. Once you know the ample cone, you're just simply, you know, taking an infimum over some cross section of the ample cone. So once you have the ample cone, you've reduced it to a minimization problem. So it's not so hard to do. I actually do not know of a polytope interpretation of the volume in this context. It seems like a very natural quantity, but I don't know how to sort of enrich this numerical calculation to something involving polytopes. So if you know about toric varieties and are interested, I'd love to talk to you about it. Okay. In any case, so just like for the volume function for divisors, we'd like to understand the strict concavity via some Zariski decomposition. Okay, and here's the way to do for this function. So again, let's suppose that alpha is a curve class in the interior of the pseudo-effective cone of curves. Then a Zariski decomposition for alpha is an expression alpha is equal to b to the n minus 1 plus gamma. So it's the sum of, so here this is called, you know, this is the positive part, and the other part is the negative part. So let me tell you what these two pieces are. So here, B is a big enough R divisor. Gamma should be a pseudo-effective class, so it's in the pseudo-effective cone of curves. and b dot gamma is equal to 0. So these are the conditions which define a Zariski decomposition. So we have some big enough part which is orthogonal in some sense to this negative part here. Okay. So if you're familiar, well, everybody is. So if you think back to the Zariski decomposition for surfaces, this is sort of word for word a generalization of the Zariski decomposition for surfaces, right? So if you have, at least if you have a curve in the interior of the pseudo-effective cone, this orthogonality to a big enough divisor is exactly the same as saying that the negative part has negative self-definite self-intersection matrix or whatever. So it really is, a generalization of Zariski's original construction in a very direct sense. So let me just make a brief remark. So here, this B realizes the infimum in the definition of vol hat. So if you go back to the definition of vol hat, there's this infimum here. It turns out that this, if you pass from ample to big enough, this infimum is actually achieved, and it's achieved by this big enough divisor here. And the other remark is that also, in what sense is this a Zariski decomposition? Well, one sense is that it preserves all the volume. So, once you've taken part 1 for granted, part 2 is pretty clear, I think, just by taking intersections. So somehow it's, some positive part which is retaining all the volume or all the positivity of A, of alpha. Okay. No, it always happens. So that's the next theorem. Let me write that down. It's a good question. So the theorem is that every alpha in the interior of the pseudo-effective cone of curves of any smooth projective variety admits a unique Zariski decomposition. Okay, and this is actually, it's just convex analysis. So it's true, in more generality. You don't need C. You don't really need smooth. If you work over C, then you don't need smooth. In fact, it's even true in the Kähler setting. So it's a very, it's just some. If you have a smooth variety, then yes, it should be true and positive characteristic. I don't know about C. This part should be fine. Other parts, I don't know. Yeah. So, we're just starting. There's a lot more to say. So, furthermore, it captures the strict convexity. So it sort of accomplishes exactly what we want it to do. So, for alpha and beta in the interior of the pseudo-effective cone of curves, we have that the volume of alpha plus beta to the n minus 1 over n, excuse me, is at least the volume of alpha to the 1 over n plus the volume of beta to the 1 over n. N minus 1 over n. So it's n over n minus 1 concave with equality if and only if the positive parts are proportional. Okay, let's do one more example. I think this is a very natural construction, so just trying to convince you that it makes a lot of sense. Many of the theorems that you're familiar with the Nakayama-Zariski decomposition, also will hold true in this setting. So it has a very clean birational behavior. The negative part is rigid in some sense, and so on. Okay. Anyways, let's do one more example. So here, let's suppose that X is a hyperkähler manifold. And I'll let Q denote the Beauville-Bogomolov form induced by duality on N1 of X. Okay. Then if we take a curve class and we write its Zariski decomposition as so, then the Zariski decomposition is exactly sort of expressing the orthogonality of the Beauville-Bogomolov form. So, and it's doing it in exactly the analogous way as divisors. So let me say this. So first of all, if you take the positive part against itself under Q, you get the volume of alpha to the exponent which works. Is this the right one? Yeah. Okay. Second of all, with respect to Q, gamma against itself is negative, so long as gamma is not identically 0. And then the third property is that the positive part and the negative part are indeed orthogonal with respect to the Q pairing. Okay, so if you're familiar with the story of divisors as developed by Huybrechts and Buxom, exactly the analogous things go through with no change. So, it really is giving you a useful way of getting your hands on the geometry in this situation. No, so you can't get that, but gamma is the push forward of a pseudo-effective cycle on a proper subvariety. That's the right analog of saying that it's actually effective somehow.
But you have examples
where it's not effective. Yes, that's right. Yeah, so there's too much to hope for, but somehow saying that it's pushed forward from a proper subvariety is good enough. Somehow, that's usually what you care about. It's a subtle property, but it's the right one, I think. I don't know how to do it for the boundary. That's a good question. The limiting behavior as you go to the boundary is very subtle. But I didn't try for a long time. It might be possible. I just don't know how to do it. Mm. Mm. That's a great question. I've wondered the same thing. So I would, yeah, it's a question that I think would be good to answer, but I haven't done it yet. So, yeah, good question. Yeah. Okay. So this is sort of one side of the picture. This is convexity. Next, I'd like to talk about asymptotic geometry a little bit. So for divisors, question? Yeah, sorry, Joel. Yes. Gamma is just some class orthogonal to B. I mean, it depends on what alpha is. You mean B is always big in F in this setup? Okay. No, it's fine. Okay. So when we talk about the asymptotic geometry of a divisor, we always mean to study its section ring, right? To study the behavior of sections as you increase the coefficient of the divisor. And this is sort of a well-studied story. But for curves, there's no easy analog, right? There's no dictionary between, say, vector bundles and effective cycles, at least not one that I know of. So we have to take some sort of different approach if we'd like to understand the asymptotic geometry. So, so here's a suggestion by well, let me say this. So for a divisor L, we can interpret the dimension of the space of sections of L, I guess -1, as the number of general points we can impose on elements of the linear series associated to L. So what do I mean by this? Well, I just mean that if you take a linear series and you ask what are the divisors in that linear series going through a general point, that's just a hyperplane, a codimension 1 hyperplane inside of that linear series. Right? A general point imposes one condition. So if you intersect these hyperplanes down, the number of general points you can force a divisor to go through is the same, in a linear series, is the same as the dimension of the linear series, more or less. So then there's a suggestion by Debar, Ein, Lazarsfeld, and Voisin is to use this interpretation for cycles. That is, instead of trying to generalize it like this, maybe we can use this side of the board and try to understand positivity this way. Okay, so let's make that into a definition. So for a curve class, and now I want to insist that it's in the lattice, which corresponds to actual 1 cycles. Let's define the mobility count so the mobility count of alpha is defined as the largest non-negative number such that there exists an effective cycle, or an effective curve, I should say, of class alpha through B general points of X. Okay, so it's exactly the analogous definition. We're asking, if you look at cycles of this class, how many general points can we put it through? And this is supposed to be an analog of H0. And maybe one of the takeaways from the talk, if you don't remember anything else, is that this works way better than it seems to have any right to. So yeah, you seem to get an interesting theory by sort of systematically doing this. Okay. So we're interested in the behavior of MC of M alpha as M goes to infinity. Right, just like for divisors, we'd like to let the coefficient here increase and see what happens, see the growth rate. That's the analog of what happens for divisors. Okay, let me just state this as a fact. There exists some constant such that the mobility count of M times alpha is bounded above by the constant times M to the n over n minus 1. Okay, it's a little bit surprising perhaps to get a non-integer exponent here, but this is really the growth rate. So maybe I should make a heuristic argument at least. So, so I'm saying not just that that we have a bound like this, but that's every variety has this growth rate achieved by maybe a complete intersection class or something. So the heuristic for this is to look at complete intersections of degree D divisors in Pn. Okay, so a degree d divisor goes through on the order of d to the n over n factorial general points. Right, the number of points that you impose on a divisor is about h0. Okay, so now if you intersect them, so if you look at a dimension k, or I'm sorry, we want to go down to dimension 1. We're not doing cycles, we're doing curves. So if you look at the dimension 1 complete intersection, that will have degree d to the n minus 1. And again, it will go through about d to the n over n factorial general points. Right, each time we remove each time we cut down by a divisor, we're shrinking the number of points by 1. But that's minuscule, we're doing that just, n times, that's minuscule compared to d to the n. Okay, so this is sort of the heuristic justifying this growth rate. Okay. So now let's let's capture the asymptotic rate of growth. The mobility of alpha is, so it's the analog of the volume. It's the lim sup, as m goes to infinity, of the mobility count of m times alpha. We'd like to compare how it grows against m to the n over n minus 1. And then again, we include a rescaling factor, as usual. Okay. There's also a version allowing for weights. Do I have an hour? Okay, then I'll talk about it. Great. So there's two versions of this construction. This one is a little bit easier to state. Let me give the other one because I'll refer to it later also. So there's also a version which allows weights at the singular points. Okay. So why would you want to do something like this? Well, so what we'll do is when you have a curve which is singular, and we'll count the singularity for more. And the reason that we do that is because it better reflects the intersection theory on the blow-up. Right? If you have a curve which is very singular at a point, and you blow up the point, it looks very different than if you have a curve which is smooth through the point and you blow up the point. Okay? So by sort of allowing ourselves to count singular points with additional weight, we can get something which better reflects the blow-up of the intersection theory on the blow-up of those points. Okay. So this definition is a little bit harder to grasp at first. So the weighted mobility count of alpha is the supremum over all positive integers mu of the number of general points in a curve of class mu times alpha with multiplicity at least mu at each point. Okay, so again, you're counting the number of points that you can impose on a curve, but here you're imposing a multiplicity of those points, and you're also rescaling the class. So, and then, the weighted mobility of alpha is the lim sup, as m goes to infinity, of the weighted mobility count of m times alpha over m to the n over n minus 1. No rescaling factor this time. So, I think it's hard to grasp what this means when you first look at it. It doesn't look like much. The point of the definition is that it's supposed to this particular weighting is supposed to pick out Sysadry constants. So as we'll see soon, you can exactly calculate the weighted mobility using the theory of Sysadry constants. Anyways. So then let's write down a theorem. The mobility function and the weighted mobility function extend to continuous n over n minus 1 homogeneous functions on the entire space of curves. Okay, so we see that some of the useful analytic features of the volume can also be recovered in this circumstance. So in particular, the mobility of a curve is positive precisely when that curve lies in the interior of the pseudo-effective cone of curves. So this is somehow describing, some sort of common geometric feature of the boundary of the cone of pseudo-effective curves. Okay. This theorem also holds in much more generality. So this is actually true for arbitrary cycles. And X can be over any algebraically closed field. It can be arbitrarily singular. So this is because the setup doesn't use vector bundles or line bundles in any way. It's actually very flexible. And I think that's sort of a key feature of this theory. Okay. Let's look at a couple examples. So the weighted mobility can be computed using Sysadry constants. For example, for H an ample divisor, it turns out that the weighted mobility of H to the n minus 1 is just H to the n. So again, we're getting sort of an intersection feel to the definition of the weighted mobility. To calculate the mobility is much harder. So unfortunately, it's much easier to define, but at least thus far, it's much, much harder to calculate. So let's do the first example, which is P3, and alpha is the class of a line. Okay, and let's ask, what is the mobility of the line class on P3? So if you sort of work through the definitions we wrote on the board, essentially what this is asking is, what is the minimal degree curve through B general points of P3? Okay, or what is the minimal degree of a curve through B general points in P3? Okay, it's a very natural question. So what's easy to show, and I guess I've sort of referred to this already, that the degree grows asymptotically like some constant, and then since I've switched to the roles of D and B, here it's B to the 2/3 instead of D to the 3/2. So it grows at some rate like this. What's hard is to exactly determine the constant C. Okay, to construct upper bounds, you just need to find curves through B general points. But to construct lower bounds is quite subtle. You need to show the non-existence of a curve through B general points. So the first guess you might do is you might look for large dimension components of the Hilbert scheme. Right? If you want to put a curve through lots of points, the natural thing to do would be to try to choose a large, well, maybe a large component of Qiao and use those curves. But let me note that the largest components of Qiao parameterize planar curves. Okay? And a curve that's contained in a plane can only go through 3 general points, the same number of general points that a plane can go through. So the difficulty of this question is coming from the fact that the largest components of Qiao just simply do not work. And similarly, you can't just step down a little bit. The largest components of Qiao will always be contained in low-degree hypersurfaces. So the conjecture, this is due to Perrin, guiding this situation, is that the optimal curves, in some sense, are always complete intersections. Okay, so it's a remarkable conjecture, right? P3 has lots and lots of curves which are very difficult to understand, but Perrin is conjecturing that the ones which are the best from the perspective of our question are also the simplest ones. So if true, this would imply that the mobility of alpha is equal to 1, but I don't know what the mobility is. You can prove it to within some small factor, but to determine it precisely is pretty hard. So let me just point out, where is this coming from? This is coming from the Gruson-Peskin bounds on genus. So it's not just something that he cooked up. So if you look at a curve which is not contained in a hyperplane of low degree, then the ones with the largest genus are the complete intersection ones. And so, thus, perhaps they should also have, they should also deform the most. Okay. Anyways, so now we have a couple different functions for curves floating around. So let's compare them. So again, this is joint work with Jian Xiao, and this is building on earlier work with Mihai Fulger. So this says that for alpha, in the interior of the pseudo-effective cone, we have, first of all, the volume of alpha is equal to the weighted mobility of alpha. So this sort of mysterious looking function, which was calculating sort of the asymptotic behavior of point counts, this sort of asymptotic enumerative behavior, exactly coincides with this function coming from abstract convexity theory. Okay. Then we can also compare against the mobility. So, of course we can't say it too precisely, but at least we get, sorry. So, at least as functions, the volume and the mobility have similar, they're sort of within bounded difference. But third, they're actually equal if we assume a special case. So what is this special case? Conjecture star is essentially the special case of a complete intersection. So for H ample, the conjecture states that the mobility of H to the n minus 1 is equal to H to the n. Okay, it's the same pattern we've seen for the other curves, for the other functions. We don't know it yet for the mobility, but if it's true, then you can determine that these two are the same all of the time. Okay? Let's see. So, what is this theorem saying? I mean, the moral, in my mind, sort of the surprising thing about this is that in some sense, complete intersection curves are distinguished by asymptotic enumerative geometry. So let's remember how this function behaves. If you take an arbitrary curve class, this function is determined by some sort of projection to a big enough divisor raised to the n minus first power. Okay, that says that this is also the same for this function. And that's highly non-obvious to me, that somehow, the curves which are complete intersection, this is saying that the volume of alpha, the weighted mobility of alpha is determined by the weighted mobility of a complete intersection class lying beneath alpha in some sense. So I find that a bit surprising. And again, the expectation is that not just for curves, but for cycles, a similar pattern seems to be emerging, but we're still quite far away from understanding it. So in the remaining time, let me maybe just say one more thing. So one application of this theory, it sort of came out as we were working through this, is a stronger version of the paper by Buxom, Demailly, Pound, and Petronel. So the theorem says that the positive product determines a continuous bijection. So this should go from the movable cone of divisors, let's say the interior of the movable cone of divisors, to the interior of the Neff cone of curves. So this is sending a big and movable divisor L to its n minus first positive product. Okay. So the theorem of Buxom, Demailly, Pound, and Petronel says that curves of this form generate the Neff cone. Right? If you look at the closed cone generated by such curves, you actually get the Neff cone. So this is saying something much stronger. You don't need to take sums. You're actually getting a bijection on the nose. So this is sort of coming from the strict concavity that I had on the board earlier. So we can get some interesting, a few interesting things from this. For example, as a corollary, we see that the rays over irreducible curves which deform to cover X are dense in the Neff cone. Okay, a priori, it's very difficult to determine if a given numerical class contains an irreducible representative or not. It's a very subtle question. And even more, you'd like to know that the cone of moving curves is actually the cone of moving curves in some strong sense. And so you can, this is sort of an easy corollary of that. So maybe let me do one more example. So let's suppose that X is a Mori dream space. then we can pass the chamber structure on the movable cone of divisors to the Neff cone of curves via this positive product. Right? So, you know, the movable cone of divisors has some natural chamber structure, which again everyone here is familiar with. And there's this question, how would you try to understand the same structure if you're focusing on curves? So if you just take the duals of the cones, this doesn't help, right? Because if you take the duals of the cones, you're leaving the pseudo-effective cone of curves, and it's not clear what those should represent. But if you take the n minus first product, what you lose is that the cones are no longer convex. You know, they might be star-shaped somehow. Even for something like a torque variety, this can happen. But you know, you still get a very clean description of the birational behavior of you know, curves on birational models of X, you know, by using this chamber structure on the cone. And things like this really come up, right? So, for example, there's this recent paper by Greb and Thoma looking at stability conditions. Or you know, stability on sheaves defined by intersecting against movable curve classes. And they come across this problem that, you know, if you follow a line, it's just not true that h to the n minus 1, if you follow a line, it's not true that all of those are ample divisors to the n minus 1. You can leave the cone. You know, so issues like this really do come up naturally. Anyways, let me stop there. Thanks for your attention. Yeah, Yoshinori? So the mobility and the weighted mobility, yes, those you can define for arbitrary cycles. That's right. This convexity part, I don't know. You know, the signature of the, you know, somehow lying this convexity is a Hodge index theorem, right? But the signature changes when you look at cycles of intermediate codimension. I don't know if some sort of convexity is a reasonable thing to expect or not. But at least in terms of counting points, you can still define the functions. Yeah. I would want to define a Zariski decomposition as a failure of strict, you know. So Mihai and I define some sort of weak decomposition where you're given a class alpha, you write it as p plus n, where this part is movable, this part is pseudo-effective, and the mobility of alpha is equal to the mobility of p. So again, it's some sort of, you know, you retain the volume in some sense, but it's on some better behaved positive part. So, you know, this is something that I didn't have time to talk about. It plays an important role in this comparison theorem that I wrote up earlier. You know, it's weaker because this is, you know, saying that a curve is movable is not the same as saying it's a complete intersection. So for curves, the version I wrote down is better. But in general, this is the best we know right now.